Okay, this is lesson 6-13, improper integrals. This is the last BC lesson of integration in terms of integration techniques and tools. Okay, so first of all, I guess we have to figure out what is an improper integral if we're going to learn how to integrate it. So an improper integral is, basically there are two types. One type is if we have a bound of infinity. So you could have the upper bound being infinity, the lower bound being infinity, negative infinity, or you could have both bounds being infinity. So that's one type of improper integral. A second type of improper integral is whenever we integrate a function. Let's say we have regular bounds, but perhaps the function is not continuous. It's discontinuous somewhere in between those bounds. So at this point, x could not be 2. And so that's an improper integral, because to evaluate integrals, the function has to be continuous from the lower bound to the upper bound. And so in all of these cases, the function is not continuous, or at least with the infinity ones, it's continuous, but there's not an actual stopping point. So we're going to figure out how to evaluate these, and we're going to look at 4 examples. And here is the first one. The integral of 1 to infinity of 2x dx. Okay, so the way we're going to do this, since we cannot evaluate an integral at infinity, we're going to use limits. And so we'll draw a little arrow here to show that we're leading to this new thought. We're going to say the limit as b goes to infinity. I chose the letter b because b usually represents the upper bound and a represents the lower bound. So the limit as b goes to infinity of the integral from 1 to b of 2x dx. Then we will go ahead and integrate now to x. So that's going to be the limit as b goes to infinity of x squared evaluated from 1 to b. Then we will evaluate that. So the limit as b goes to infinity of b squared minus 1 squared. And then as we evaluate that limit, we'll get infinity minus 1, which is infinity. Now, just like whenever you first learn limits, and whenever you would get an answer of infinity for a limit, you would say it does not exist. Whenever we evaluate integrals and we get an answer of infinity, we don't necessarily say infinity is the answer. We say that the integral diverges. Diverges means that it keeps going to a number that doesn't land. It never stops. It's not... Yeah. So this is actually a really important part as you continue Calculus BC. The very last unit, Unit 10, looks at sequences and series, and divergence and the opposite of that, convergence, is very important. All right, so there's the first example. Here's the second example. Let's find the integral from negative infinity up to 4. So you can see I put the infinity sign as the lower bound of x to the negative 2 dx. Okay, well, since it's the lower bound, we're going to say, okay, so this leads to the limit as a goes to negative infinity of the integral from a to 4 of x to the negative 2 dx. All right, and so we're going to go ahead and integrate that. So x to the negative 2 will become, well, let's see, negative 1 over x, or negative x to the negative first power, if you want to put it back into a negative 1 over x, evaluated from a to 4. So we're going to go ahead and evaluate that. So we have the limit as a goes to negative infinity of, well, let's see, negative 1/4, and then minus a negative, so 1 over a, plus 1 over a. And now let's plug in that negative infinity. So, well, let's see. As we divide anything by infinity, it gets closer and closer to 0. So this limit ends up being negative 1/4. Now, we actually got an answer. So we give that answer. Now, this is an example of an answer that converges. We would say this integral converges to negative 1/4. Now, we don't just say it converges and that's it, though. Whenever an integral converges and we can give the answer, which in this case we should be able to, we actually want to give the answer. Again, this is a really important concept that you'll deal with later in the class. All right, let's look at a third example. This time we'll look at an example of two bounds are infinity. So negative infinity to positive infinity of 2e to the 2x dx. Okay, so I want you to think about this for a second. So what happens is negative infinity is some very small negative number and positive infinity is some very big positive number. We need to split this up into two separate limits. Let me show you how we're going to do this. We're going to say, okay, the limit as a goes to negative infinity, and we're going to evaluate the integral from a, but we're not going to go up to positive infinity. Think about a basic integration rule is that, let's just imagine you had the integral, say, of 1 to 5. Well, you could split that and say the integral of 1 to 3 plus the integral of 3 to 5. Just basic addition, and that's allowed. So what we're going to do is we're going to pick a number between negative infinity and infinity. Now you could pick an actual number. 0 is great, or if you want to stay kind of theoretical, you could just let c, where c is just some number, and any number would be between negative infinity and positive infinity, so it doesn't really matter what it is. So we're going to take the limit from negative infinity up to our number somewhere in between infinities of 2e to the 2x dx. Then we're going to add to that. We need to go pick up from our number and go up to positive infinity. So the limit as b goes to positive infinity of the integral of our number that we chose going up to b of 2e to the 2x dx. So you have to do two limits of two integrals here. Now, the good news is that it's the same integral, so you only have to figure out the integral part once. And this is an integral we need to just sit and pause and think about for a second. It's not quite super straightforward, although if you've done enough e integrals, you might be able to see the integration of this without using substitution. But I'm going to go ahead and use u substitution to show you this. So I'm going to let u be 2x. The derivative of u is 2 dx. And if I solve for dx, I get du over 2. So these both will change to the integral of 2 e to the u times du over 2. Our 2's cancel out. These are e to the u du is what we're taking the integral of. And so the integral of e to the u is e to the u plus c, of course, but we have bounds, so we're not going to worry about that. And so that becomes e to the 2x, which is what our u is. So now I can rewrite these integrals. I'm going to say the limit as a goes to negative infinity. The integral of a, well, actually we don't need the integral. We actually know it's e to the 2x, so e to the 2x evaluated from a to c. Then we're adding to that, picking up from the other side of c, the limit of b going to infinity of e to the 2x from c to b. All right, so let's evaluate these. The limit as a goes to negative infinity. I'll use a parenthesis because I have two things here. It's going to be e to the 2c minus e to the 2a plus the limit as b goes to infinity of e to the 2b minus e to the 2c. And let's evaluate those now with our limits. So remember, c is just a number, so it's not a variable. So e to the 2 times a number. That's e to the 2c. Minus e to the 2 times negative infinity. I'm going to plug in negative infinity for a. That 2 times negative infinity is just negative infinity. Of course, a negative power puts us on the bottom of a fraction. So 1 over e to the infinity. All right, plus this is e to the infinity whenever we plug b in, minus e to the 2c. All right, you should see that we have e to the 2c and minus e to the 2c that cancel out. You should see that this becomes 0 and this becomes infinity, and so that leads us to infinity, which means that this integral diverges. Remember, I'm going fast. Pause as you need to pause. Sit and think out things. Write down the steps. Work it out. Don't just watch it. All right, and finally, we need to go to the other type of improper integral. Let me go back to the top here. We said there are 3 improper integrals just with infinity, depending on where you put your infinity. And the 4th improper integral is whenever you have a finite number of discontinuities. What do I mean by that? Well, finite means that you can count the number of discontinuities. So in this case, this example on the screen right now, we have one discontinuity, right? X cannot be 2. That's one place that this function is discontinuous. So here is an example we're going to do. We're going to take the integral of -2 to 1 of 1 over x squared dx. Okay, so I want to find my discontinuity, and I know that x cannot equal 0 here. So since 0 is my discontinuity, we're going to use the same idea that we did whenever we have both of our bounds being infinity. We're going to split it up into two integrals that we're going to add together. And we're going to go from -2 up to 0 from the left side. Then we're going to add to that the integral of 0 from the right side up to 1. So that involves limits. So we're going to say, okay, the limit, and we're going to go up to the left side of 0. So as b goes to 0 from the left side of -2 to b, well, I'll tell you what, let's change that to x to the -2. I think it's always easiest to use negative exponents in the numerator than in fractions. And then we're going to add to that to the limit as a now goes from 0 on the right side. So that's the integral from a up to 1 of x to the -2 dx. Okay, so two limits, two integrals, but it's the same integral, so you only have to think through the integration once. So here we go. We're going to have the limit as b goes to 0 from the left side. The integral of x to the -2 is -1 over x. And we're going to evaluate that from -2 to b. Then we're going to add to that the limit as a goes from 0 on the right side. And the same antiderivative, -1 over x, evaluated from a to 1. All right, let's evaluate the limit as b goes to 0 from the left side. Whoops, I have a -1 on that left side on the last step. I don't know why. I'm going to get rid of that. So here we go. That is going to be -1 over b minus -1 over -2. So that's three negatives. We'll make it -1 over 2. And then we're going to add to that the limit as a goes to from 0 on the right side, or to 0 on the right side, however you want to think of it, -1 over 1 minus -1 over a, so plus 1 over a. So whenever we plug in 0 from the left side, that's a negative number, getting very close to 0. Negative over negative makes positive. 1 over a very, very, very small number is positive infinity. Then we have -1/2. Then we have -1. And then 1 over a very small decimal gives us positive infinity. So we have a couple of infinities. Just make infinity. -1.5 doesn't matter. Stays infinity. And that one diverges as well. I will say one more thing. Sometimes the bound will be the discontinuous point. And at that place, you don't have to do two limits. You just do the limit from that bound or up to that bound. All right, there you go. Thanks.